Hello, welcome to Essentials of Computer Architecture. In complement to what we will be covering in our class, I'm going to do relatively short summaries of each of the chapters that we will be covering. The material is coming from these charts that I'll be using. This is based on Douglas Coomer's original slides, and if you want these PowerPoint slides in PDF form are made available in the class, and you can look at the original version. There's a link here. So let me today I'm going to give an introduction to the textbook and a little bit of orientation, and then I'll just get into chapter 1. So from the textbook, these are what the material. Here are the chapters. There's a total of 23 chapters and 4 appendices. And for the most part, we're going to be going through all of the material in the textbook. And I would point out that there's really 3 main sections that we'll be focusing on. We'll be focusing on processors, and so that's part 2. Memory, so that would be the second part, and then I/O, input and output. There are basics that we need to cover to help us get into these 3 major components, these 3 major areas in computer architectures. And so we'll cover that with these these 3 introductory chapters. So today we're going to be talking about chapter 1, and I can easily go back and forth in different areas within these charts. That's what the blue shows, but for now, we'll just move on. So Douglas Coomer is the author of our textbook, Essentials of Computer Architectures. It's a very accessible book, and if you want to have a very orderly way of looking at the material for computer architecture, I think it's an excellent resource. There's an optional textbook, Computer Organization and Design, that is a little higher level and gets more into the application, which is also something I would recommend you get a chance to look at. So there are various computing platforms that are out there, and I'm just trying to graphically give you an idea of what that landscape looks like. Most of you, I'm sure you're familiar with various types of computing platforms. You probably have a laptop in front of you as you're looking at the material, viewing this lecture. And so I'm just giving a couple examples, whether if you're looking at a Windows-based machine, and so I'm just illustrating an example of that with the Microsoft Surface that has slowly evolved and has had multiple generations that have been out there. Another architecture that is not Windows-based, that is based on a Unix operating system, BSD, is the MacBook series, whether it's a MacBook Pro or other platforms. And so oftentimes those are very common platforms. I'm not showing Chromebooks or other things like that. In terms of phone, maybe you have an iPhone and Android of some sort. And so there's the desktop / laptop type of computing. There's the mobile computing platforms that we have, and there's multiple processors that they have inside. For the desktop applications, it's typically has been either an Intel-based or an AMD, which at a medium level, they're compatible with one another, that the operating system can be set up such that they can use either an AMD processor or an Intel processor. And this is using something called the x86 architecture, which used to be 32 bits. Now 64 bits is where the sweet spot is at. But there is a movement now, both Apple has announced and Microsoft has one of its services that is now using the an ARM based type of instruction set, and we will be getting more into that as we go. So just giving you a rough idea in terms of some platforms that you might be familiar with. You may also have a tablet of one sort or another. In relatively recent times, Apple created a tablet that has really broken that market open. And so now there is a variety of platforms from a number of different manufacturers, but I'm showing an iPad here on the bottom. We will be dealing with a platform called an Arduino. It's interesting in a couple different ways. It's a open source hardware and software, so you can easily just get the specs for the hardware, and a number of manufacturers have Arduinos that are based on their open source criteria and have slight variance. And so that's what I'm showing here. A Raspberry Pi may be something that you've heard of as well. It uses an ARM processor. An Arduino does not. It uses a microcontroller, and we will actually be programming an Arduino in part of our course work. And up here, I'm showing some things that are developing, dealing with cloud storage and computing. When you're mobile or even with your desktop environment, a lot of times that you're getting a lot of connectivity with cloud computing and cloud resources. And so that's a very common thing that you at least have experienced. You may not have figured it out or thought very much in detail. And another thing that is starting to happen is the Internet of Things. 5G technology is an enabler potentially that just about anything, whether it be your refrigerator, different parts of your home environment, that could wirelessly be connecting with infrastructure and communicating and providing some interesting new capabilities as we go. Well, that's enough just for a quick orientation. Now I'll start walking through the material that Kumar has laid out, and we're customizing that for what we'll be covering in our class. The class is Kumar Talks to Computer Scientists, but this is a cross-listed class, so computer scientists as well as engineering majors will find some very interesting things to be thinking about as we're covering this material. So most computer science programs require an architecture course, and this is what we have as part of your curriculum in your program. And the questions that Kumar wants us to be thinking about is knowledge of computer organizations and the underlying hardware relevant these days? Should we even take this kind of a course seriously? And it's an interesting thing to be considering. But if you look at a lot of the companies that are hiring computer scientists, they will be looking for your knowledge of architecture. If you understand computer architecture, this will be helpful for you to be getting a job, which I'm sure you all are looking for ways of how to be getting your first job and being successful in that. Most successful software engineers understand the underlying hardware and know about architecture, and this can be helpful as you develop your career. And as a practical matter, knowledge of computer architecture is needed for later courses as you go on in your program. Some of you may want to be doing graduate work, and so if you get involved in system programming, design of compilers, considering operating systems or embedded systems. So that's just a couple things for you to be considering. So according to Kumar, his point of view is traditional software engineering jobs are saturated, but there's a lot of these other types of platforms that are out there, and programming for a mobile device, whether it be your iPhone or an Android type of platform. There could be various types of video interfaces, and interesting things that are starting to go in that area. Media and MP3 players. There still is an interesting market. What there is sort of this um, mobile platforms and those type of players are kind of converging for the most part. But you do have things like iPads and other things that still can fit into that area. Content set-top boxes and the classical cable box that you might be thinking about. There's all kinds of different types of set-top boxes, and I'm just showing an Apple TV here as an example. And there's also could be smart sensor systems, whether it be that you have a front doorbell that has a video camera, and there's some very smart systems that are doing things in that area. So these are example of how things are changing as we move forward. So understanding architecture is key for programming embedded systems. And so that just gives you another example of why this is important. Some bad news about architecture. Hardware is complicated. Kummer even uses the word ugly to describe that. There's lots of low-level details, and it can be counterintuitive. And as we go through the course, I will give you some examples of things that I've experienced in that regard. Hardware is tricky. Timing is important, and you have to think that it takes time for even electrons, even electricity to go from point A to point B. And so that is a factor that now needs to be considered. A small addition in functionality can require many pieces of hardware. And so if you're going to be doing some functionality in hardware versus software, that's something that you'll have to be considering. And the subject is so large that we can't cover it in this course, but we want you to be mindful of that and figure and have some ways that you can bound that and realize that you personally don't have to be an expert on everything. But there's some interesting ways that you can add on capability that has been done based on having interfaces and things well defined. So those are just a couple thoughts. In terms of good news about architecture, you will be learn to think in new ways. It is possible to understand basics without knowing all of the low-level technical details. And I want to say that as a point of encouragement, that we will be trying to give you a broad introduction, a survey of some of these things. And if you don't get it all, it's okay. Let's just walk through the process and see how that works. You don't need to know how a car works to be able to drive it. But if you were to start to want to program new capability for a car, you're going to see that you're going to need to have some more understanding of how things come together. So programmers only need to learn the essentials, the characteristics of major components, the role of overall system, and the consequences for software. And so that is the thing that we will be talking about in our class. And going back to the major parts of our course, I mentioned processors, memories, and I/O and how that operates. We will be spending lots of time on that, but we'll need to give a basic introduction to what digital hardware is all about, and we'll build a few simple circuits. And so that will be, we'll get into our first project, we'll be focusing on that. Our second project will get into processors. We'll actually be looking with an emulator. We will do some assembly language programming and give you a little bit of an idea how that works. And there's basically two different types of processor categories that exist. And one is called the reduced instruction set computer, or RISC processor, and a complex instruction set computer. So there's more instruction sets that exist in the complex instruction set versus the reduce, it tries to streamline things. And so there would be more lines of code in a RISC-based processor, and there would be more flexibility at having number of instructions to be more precise at a lower level. So that's the difference there. Multiprocessors without interlocking pipeline stages, you'll hear the term MIPS, and so that's what I'm trying to introduce here. And so MIPS processors are examples of RISC processors. So that's just a little bit of nomenclature for you to think about. So just to finish up, a couple charts in terms of organizations of the course as we're doing this first chapter overview. Will give you an understanding, a taste of what digital logic is. What are digital logic components made out of? They're made out of transistors. We'll give you that idea. We'll be talking about data representation, talking about ones and zeros, talking about logic. And there are courses that you've already taken that will help you to get a basis for this, and we'll try and tie that together to make this a little bit easier for you to take this next step. Processors, we're going to be talking about instruction sets and the operands. So the instruction and the things that they're supposed to operate on will give you an introduction to what assembly languages are all about and doing the programming associated with. And we'll talk about memories. We'll talk about physical and virtual memories. It's an interesting way of thinking about it. There's the actual way things are, but when you have multiple components, what does that physical component need to know? And so there's examples, a number of different ways how virtual memories of creating ways of considering things virtually is very helpful. How do you do addressing? How do you cache? How do you put things in a easy to get nearby to start to do computations? And we'll get into details about that. Input and output, we'll talk about devices and interfaces, buses, bus addressing, and it's getting not so common now, but some of the original personal computing environments, they had ways of having you see this in more details, and I'll give you a little bit of insight into that as we go. Finally, we have the advanced topics, and we won't spend as much time on this, but we'll at least try and give you an introduction to these various ways of how you can do more elaborate types of processing with tools and architectures that are out there. So there are some things that we won't cover. We won't get into some of the most low-level details. I will mention it briefly, but the neat thing about it is you don't have to be an expert on all of these areas to be proficient in computing and programming. So we will not get into deep analysis of circuit evaluations. So that's something as well that we will not need to focus on. Design rules that specify how logic gates may be interconnected. We will not get into detail about that. We won't talk about circuit design and design tools. So we won't get into details about that, and we won't get into chip design and languages such as Verilog and VLSI, very large scale integration, how you actually lay out components in a chip. We will not be talking about that as well. So we will be talking about architecture, design, and implementation. You will see that a lot as we move through the class. So architecture refers to the overall organization of a computer system. It's an analogous to a blueprint. The specifics, there's a functionality, the major components, the interconnections. And so we will definitely be touching on architecture. And there is a level of abstraction that we can use. And so there's sort of a quote medium level that we'll be focusing on that I think will be helpful, and it'll give you a nice way of, I think, taking a lot of valuable lessons from this class. It's the design, it's needed before a digital system can be built. You have to know what you're going to design before you can actually create it. We will translate or get an idea how you translate architectures into components um, for design. It fills in details that the architectural specification omits. And what does the design do? It specifies items such as how components are grouped on the board, how powers are distributed, and many designs can be can satisfy a given architecture. Implementation, the third thing here is all the details necessary to build a system includes specific part numbers, mechanical specifications of chassis, the layout of the components, power supplies and power distribution, signal wiring and connectors. We will do a little bit of implementation, but with a set um, of components that is predefined in an Arduino kit, just to give you a little bit of an idea of how that would be. So in summary, architecture is required because understanding computer organization leads to programming excellence. This course covers the 4 essential aspects of computing architecture. The building block you start with is digital logic, and you'll see, we'll come back to that again and again to have you see that. The main part of computing is done with the processor, and you'll see why that is key. And to do that processing, it needs things, it needs memory, it needs things that can store and receive information, and we need to get things in and out of that computational core. So I think it's going to be interesting, and we will have fun with hardware, and that will definitely be a nice component. So with that, I'm going to finish this first lecture, and that'll be it for chapter 1. Thank you.